Let's talk more about hypothesis tests. The null hypotheses have special requirements. To perform a hypothesis test, the null must be a statement about the value of a parameter for a model. We then use this value to compute the probability that the observed sample statistic, or something even further from the null value, would occur. How do we choose the null hypothesis? The appropriate null arises directly from the context of the problem. It is not dictated by the data, but instead by the situation. A good way to identify both the null and the alternative hypothesis is to think about the why of the situation. To write a null hypothesis, you can't just choose any parameter value you like. The null must relate to the question at hand. It is context dependent. There is a temptation to state your claim as the null hypothesis. However, you cannot prove a null hypothesis true. So it makes more sense to use what you want to show as the alternative. This way, when you reject the null, you are left with what you want to show. In other words, the null will contain the equality of the claim, and the alternative will contain the opposite claim. Take an example. A skeptical paranormal researcher claims that the proportion of Americans that have seen a UFO is less than 4%. So we have to identify our parameter, which is P, the true population proportion of Americans that have seen a UFO. Our null is going to be P equals 0.04. The reason is that the null always is going to have an equal sign in it. The alternative is that P is less than 0.04. Since in the problem it talks about that it's going to be less than. Another example. The U.S. Department of Labor and Statistics released the current unemployment rate of 5.3% for the month in the U.S. and claims the unemployment rate has not changed in the last 2 months. However, the state statistics reveal that there is a change in the U.S. unemployment rate. What are the null and the alternative hypothesis? So, population proportion is the true population proportion of Americans that have seen a UFO. Our null is P equals 0.053. Again, it has the equal sign. And our alternative is that it does not equal 0.053. And the reason is it says that it has not changed, and they think it has changed. So it doesn't say one way or the other, more than or less than. Therefore, this is going to be a not equal sign. A p-value is a conditional probability, the probability of an observed statistic given that the null hypothesis is true. The p-value is not the probability that the null hypothesis is true. It's not even the conditional probability that the null hypothesis is true given the data. Be careful to interpret the p-value correctly. Take an example. A weight loss center provided a loss for 72% of its participants. The center's leader decides to test a new weight loss strategy on a random sample of 140 and found 109 participants lost weight. The p-value is 0.061. What does the p-value mean in the context of this problem? So the p-value means that the probability that we would get a sample proportion equaling to 109 over 140 given the population proportion equals 72% is equal to 0.061. There is a 6.18% chance of having 109 or more of 140 participants in a random sample weigh less if in fact 72% do. Sometimes we need to make a firm decision about whether or not to reject the null hypothesis. When the p-value is small, it tells us that our data are rare given the null hypothesis. How rare is rare? We can define rare event arbitrarily by setting a threshold for our p-value. If our p-value falls below that point, we'll reject the null. We call such results statistically significant. The threshold is called an alpha level, denoted by alpha. Common alpha levels are 0.10, 0.05, and 0.01. You have the option, almost the obligation, to consider your alpha level carefully and choose an appropriate one for the situation. The alpha level is also called the significance level. When we reject the null hypothesis, we say that the test is significant at that level. What can you say if the p-value does not fall below alpha? We should say that the data have failed to provide sufficient evidence to reject the null hypothesis. Don't say that you accept the null hypothesis. Recall that in a jury trial, if we do not find the defendant guilty, we say the defendant is not guilty. We don't say the defendant is innocent. The p-value gives the reader far more information than just stating that you reject or fail to reject the null. In fact, by providing a p-value to the reader, you allow that person to make his or her own decision about the test. What you consider to be statistically significant might not be the same as what someone else considers statistically significant. There is more than one alpha level that can be used, but each test will give only one p-value. What do you mean when we say that a test is statistically significant? All we mean is that the test statistic has a p-value lower than our alpha. Don't be lulled into thinking that statistical significance carries with it any sense of practical importance or impact. For large samples, even small, unimportant deviations from the null hypothesis can be statistically significant. On the other hand, if the sample is not large enough, even large financially or scientifically significant differences may not be statistically significant. It's good practice to report the magnitude of the difference between the observed statistical value and the null hypothesis value, along with the p-value on which we base statistical significance. When making a confidence interval, we found a critical value to correspond to our selected confidence level. Prior to the use of technology, p-values were difficult to find, and it was easier to select a few common alpha levels and learn the corresponding critical values for the normal model. Rather than looking up your z-score in the table, you could just check it directly against those critical values. Any z-score larger in magnitude than a particular critical value leads us to reject the null. In other words, the absolute value of our test statistic z, if it's greater than the absolute value of our critical value, we would reject the null. Any z-score smaller in magnitude than a particular critical value leads us to fail to reject the null. Again, the absolute value of z, our test statistic, is less than the absolute value of our critical value, then we would fail to reject. Here are some traditional critical values from the normal model. So for an alpha of 0.05, one-sided is 1.645. For a two-sided, it's 1.96. For 0.01, a one-sided would be 2.28. For two-sided test, it would be 2.575, and so on. When the alternative is one-sided, the critical value puts all of alpha on one side. When the alternative is two-sided, the critical value splits alpha equally into two tails. Confidence intervals and hypotheses are built from the same calculations. They have the same assumptions and conditions. You can approximate a hypothesis test by examining a confidence interval. Just ask whether the null hypothesis value is consistent with a confidence interval for the parameter at the corresponding confidence level. Because confidence intervals are two-sided, they correspond to two-sided tests. In general, a confidence interval with a confidence level of C% corresponds to a two-sided hypothesis test with an alpha level of 100 minus C%. If the parameter is in the interval, we fail to reject the null hypothesis. If the parameter is not in the interval, we reject the null. Take the following problem. Is the mean weight of female college students still 132 pounds? To test this, we take a random sample of 20 students, finding a mean of 137 pounds with a standard deviation of 14.2 pounds. Use a significance level of 0.1. Assume the conditions have been met. So we'll go right to our hypothesis. Our hypothesis is that mu equals 132. The alternative is that mu does not equal 132. We're going to use t because we don't know our population standard deviation, so we have to use t. We're going to get 1.575. Since this is a two-tailed test, we're going to shade both sides. We're going to find a p-value of 0.0576 on both sides. So the probability that we would get a sample mean equaling 137 given the population mean equals 132 is 0.1153. So we would fail to reject the null. Again, if we were to do this as a confidence interval, we would have 137 plus or minus 1.729 times 14.2 over the square root of 20. We get 131.51 to 142.49. Now our null is that mu is equal to 132. You'll notice that 132 is in the interval. Since it's in the interval, we fail to reject the null. The relationship between confidence intervals and one-sided hypothesis tests is a little more complicated. A confidence interval with a confidence level of C% corresponds to a one-sided hypothesis test with an alpha level of 1/2 of 100 minus C%.